Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth.
Hello, folks. Today we are joined by OSU Professor Dr. Michael Groeber, an Associate Professor of Integrated Systems Engineering and an Associate Professor of Mechanical and Aerospace Engineering at The Ohio State University. Nathan Ames, the Executive Director of OSU's Center for Design and Manufacturing Excellence, or CDME, and the Nomad researcher himself, Dr. Andrew Gillman, a Research Materials Engineer at AFRL, all here to discuss the future of creating stronger, more reliable pieces of equipment, both at home and abroad, by taking notes from the past via the power of the present with their project, the Robotic Blacksmith.
In 3, 2, 1.
All right, well, thank you all for being with us first today. So thank you all for gathering and talking to us about Robotic Blacksmith.
Yeah, you're welcome.
Excited to be here.
Awesome. Well, we're going to start off with an important question. So I just mentioned something interesting, a robotic blacksmith. So we're going to go to the blacksmith element of that. I want to start with you, Nate. What is your familiarity with smithies, or at least blacksmiths? Have you worked in this before, like the actual getting inside one of these spaces? Was that a passion of yours? Like, let's talk about your history with it.
Never. I have zero background with blacksmithing, robotic or otherwise. I think I've seen Forged in Fire once on TV.
Hey, that's a start though, right? So it did at least spark an interest in you then. Like you're like, you know what? I could go out there and just grab a hammer and make my own sword.
That's right, yeah. Blacksmithing is very material science centric at its core, which is my interest.
Absolutely. Well, over to you then, Andrew. Any passions with you then when it comes to blacksmithing? Do you have a history of this at all, or is this kind of your first real introduction to it?
Yeah, and honestly, starting to engage with this team at Ohio State was really got me into it. I mean, Nate's point about Forged in Fire, I remember when that came out, whatever that was now, 7 or 8 years ago.
Yeah.
My wife and I did really get into that series for quite a while, so got into some of it. You know, made the learning curve a little bit easier once we started getting deep into the science of it. Beyond that, though, inspired. We had a postdoc that was working on this project at one point. He had a date night to a blacksmith class here in town in Columbus, and I've got an upcoming date planned myself with my wife to a blacksmith class here coming up.
The inspiration, see, it continues. Yeah. That's awesome. Well, we're gonna have to see what you're making here. I know they usually start off with knives and something simple, but maybe they already see you're advanced enough. You can make like a claymore. I'm saying that could be pretty cool. That's awesome. So then over to you then, Mike. Any past history with smithies, blacksmithing?
Yeah, so I think sort of some of my youngest memories, actually, my family, we would take vacations, and on the way to the beach, my dad would make us stop at Williamsburg every year, even though it doesn't change because it's still 1700 there. But my favorite was always the blacksmith and the tinsmith, and I think I made some unwearable horseshoes one time.
Hey, you did it.
So not a full-on forge, but the blacksmithing process when I was pretty young.
That's so amazing. Hey, you had a real hand in it, though. So when it comes to early experts, you're winning. I have had no experience, but myself, you can't really see them around me, but I have a lot of weapons I've collected from blacksmiths. So I usually go to Renaissance festivals. So I appreciate their work, always wanted to do it. And that's why this sounded so cool to me. So I have a few things to learn from you guys, and so do our audience members. But that said, now we have an idea of, going past our histories with blacksmithing specifically, let's talk about your histories in STEM. So starting off with you, Andrew, what really connected you with getting to material science, like what you're doing now, I should say? Like what started as a kid till now? Was that always a passion of yours, or was it something that kind of grew in high school and college?
Yes, I was definitely always pretty mechanically inclined. Math and science were always interests of mine, things that I just did well in school. My dad was a chemical engineer, spent his entire career in the pharmaceutical industry, so engineering was in my household, always on the radar. Nevertheless, still did the full extensive analysis of like what careers could match up with me. Engineering popped up there along with some other ones. Maybe not material science stuff, but just very mechanically inclined. Was always interested in how things work, taking things apart from a very young age. Those things weren't always getting put back together, but yeah, the interest in understanding how they worked was what was driving me to take them apart.
And would you say the same is kind of similar for you, Nate? Was the idea of seeing how the world fits together, breaking it apart, or what part of the STEM journey connected with you?
So I grew up in a small town, and for the most part worked on a farm, either family or neighbors. And my dad was an engineer for the railroad, but in full disclosure, I don't think I really knew what he did. I just knew that he left for a week and came back on weekends. It wasn't until So I was in high school and started trying to figure out where to go to college. I had a cousin who worked for one of the automotive companies, and he ran the robotics lab. So my mom said, "Hey, this would be good. You think you want to go to college? You think engineering sounds interesting? We should go see your cousin." And I didn't, again, no exposure, didn't really know what robots were. Walked into his lab and saw dozens of robots all swinging around doing cool stuff. And I thought, that's what I want to do. That led me to Ohio State's welding engineering program, where they have specialization in robotics. And then again, the way life happens, I suppose, as soon as I got here, I found my way into material science, and I still did welding engineering, but I was fully focused on the material science side, like what happens when you deform material, when you heat material, kind of how microstructure changes. I didn't touch a robot until 20 years after I graduated.
Build-up's important. You had the excitement, you had the idea behind it, you had the practice. It's just a matter of time. And also seeing those armatures, a lot of the robotics in any kind of automobile setting. I mean, that had to be awesome. As a kid, as an adult, whatever. I mean, that's amazing.
Oh yeah. Massive, huge, kind of overwhelming and exciting all at the same time.
Hey, that kind of motivated me. Maybe that's what I needed early on. So my parents were aviation engineers, love what they do, but a lot of the science went over my head. So pun intended. But over to you then, Mike. What inspired you to join the STEM fields? Was this an early passion of yours, or when did it catch on?
Yeah, I mean, I think pretty similar to Nate and Andrew, just sort of always interested in that. My dad was more of the hands-on type, so he was a locksmith, a car mechanic, a bike mechanic, and so just kind of always building things. We had a big slot car track in our basement that he would build all the cars, he built the track, and so just seeing stuff get built, and then they were usually pretty fun to play with once they were built. So it made me always interested in making stuff and figuring out how they work. And so all my favorite teachers in high school and elementary school were always my science teachers. So it just kind of led me down that track. Didn't know what engineering I wanted to do, maybe leaning towards computers and things. And so I came to OSU and then found out about material science. It's not one you sort of know about usually in middle school and high school. And you kind of realize, well, everything's made out of a material, and that material can really have an impact on how it functions and what it can do. And so that just got me really interested in, maybe it was a way to sort of punt on the decision of what I wanted to work on, because materials can go into so many different fields. So I got really interested in that, and that's kind of where we are now.
Fantastic. So speaking of where we are now, let's start down the line again. How do we all connect with AFRL or first hear about it? So I'll start with you, Andrew, because I do see you have the AFRL hoodie on right now. So how did you originally connect with the organization?
Yeah, I heard. Came prepared with our official AFRL apparel.
I clearly messed up. I should have worn mine.
No. Anyway, though, yeah. So what I had to mention, did my undergrad at Purdue in mechanical engineering with the mechanical inclination. Went to then graduate school for a PhD program in mechanical and aerospace engineering at Notre Dame. That's just where I first started to hear about AFRL. A big portion of my PhD research was funded through the SBIR and STTR program at AFRL, but actually out of the munitions directorate, headquartered out of Eglin. I didn't have a ton of contact with AFRL personnel, but just the name, the acronym at least was on my radar, and I had a small window into what they were interested in, but still had no idea that AFRL was headquartered in Ohio until I finished my PhD in kind of computational mechanics and engineering, and was prioritizing looking at jobs in government labs in the Midwest, and all of a sudden a lot of jobs started popping up that fit my background here at Wright-Patterson, and so took a kind of contractor postdoc type role for a few years there, working with a good team in the functional materials area at AF. And then when a new team got going on now, the digital manufacturing research team, with some open civilian researcher slots, I kind of jumped at that opportunity just under 5 years ago now in early 2019. Got connected with kind of as AFRL, got connected with OSU shortly thereafter, and kind of everything else is history since then.
Wonderful. And that answers our question too, how you help connect with the OSU. So over to you then, Mike. How did you connect either with AFRL first, OSU, or a combination of both?
So I'm a Central Ohio kid, sort of growing up in Springfield, sort of halfway between OSU and AFRL. So I guess the center of it all, if you will. So even as a kid, I remember coming down to Wright Pat to go to the Air Force Museum. So I don't know if that was just because it was a free thing to do for me when I was a kid and my parents get me out of the house, but used to love walking around and seeing everything there. I had no idea there was then a lab doing stuff behind it. I just assumed all those buildings were to take care of the museum, I guess. So then went to school over here at OSU for undergrad, and then stayed for grad school because I was working with a professor in undergrad who then got a project with AFRL. It was one of these workforce development research kind of combo type programs. And so I was working with AFRL, spending my summer. So I would drive down every day in the summer. I had two mentors at the lab that were fantastic. And so I loved going down to the lab. There was a multi-million-dollar microscope that I used, was sort of given to me. And so when you're a grad student and you realize how much resources are available at the lab, it was an awesome place to be. The people were great. The equipment was great. And so I spent a lot of time down there, and it just got me excited. I ended up taking a postdoc position like Andrew did at the lab, and then ultimately transitioned to be a civilian there. And so I spent a decade of my life as a civilian after spending sort of 6 years doing a postdoc and a lot of my grad work down there. Loved it, loved working there. And then an opportunity opened up back at my home institution at OSU. And it kind of gave me an opportunity to, you noted Andrew was wearing his hoodie. My invisible AFRL hat has never come off, right? It still sits underneath my invisible OSU hat. So it was kind of like becoming an AFRL employee outside the fence over here at OSU. So I still do a ton of work with AFRL, and that connection has never gone away.
And that's a great point to make too for a lot of our listeners, is people always question like, hey, at AFRL, like what is something you can do after the fact, or can you still connect while doing the same mission? The answer is yes. And a lot of that is through academia and this kind of research. So thank you for sharing that part of your story, because many people have that question of, well, how do I stay connected? Doing what Mike's doing. So that's awesome. So over to you then, Nate. Same question. How'd you connect with AFRL, OSU, or both?
So my story's a little bit different. I did undergrad and grad school here at OSU. And for whatever reason, I did not know AFRL existed. So I was out of university, kind of doing my day job, before I figured out that AFRL wasn't enlisting in the Air Force. Got engaged with both the Air Force through AFRL and the Navy through its lab counterparts in my career after graduation. And then when I finally had the opportunity 9 or 10 years ago to come to OSU, it became kind of a secret mission of mine to figure out how to get OSU and AFRL connected better. We're an hour apart. Everybody on campus, students included, should all know AFRL inside and out. And I'm trying to do what I can. Thanks to Andrew and his team, I was given the opportunity to come in as a contractor. So still an OSU employee, but a contractor with AFRL a little over a year ago. And that's been great in terms of exposure for at least the students in the center and the faculty we work with Andrew's group and others on base. It's been amazing. Right? I think we're making great strides, and this podcast is kind of testament to it a little bit.
No, absolutely. And again, very appreciative you guys can share this with us. One of the most important parts of this podcast is knowing where you guys come from, so people can see if they can follow in the same footsteps or kind of mirror different career goals. So that really does help set the scene for folks for who you are and why we're here today. The Robotic Blacksmith Project. What is it exactly, and why would AFRL or the Air Force need something like this? And also, just what is it? I'll start with you, Andrew, to start breaking into it.
Yeah, I'll start. Kind of robotic blacksmithing is kind of the colloquial term that we've been using, that we think resonates with a lot of people. But a lot of, I guess, our motivation for kind of the prototype systems that we've been developing really kind of come out of a concept of metamorphic manufacturing, which was introduced, I think, about early 2018, leading into 2019, was put out by the TMS Society, Very Active Materials and Manufacturing Centric Society, that created this vision of what would a kind of incremental forging process look like that had an agility to incrementally forge parts in a similar way to additive manufacturing, where you're kind of incrementally melting parts. I think this kind of study came about just given where a lot of the technology was at the time, right? There was a lot of good sensors that were being developed, not just for manufacturing, but for things like autonomous driving. We had the traditional tools like induction furnaces, ovens for heating our material, and any artisanal blacksmiths workshop today, you'll see in our artisanal forge press for getting that deformation in the systems. Just with the state of both robotics and artificial intelligence and machine learning, with the hope of that could provide the flexibility and agility to actually, have a relatively closed autonomous cell that could make a variety of number of parts. You could easily begin to envision this autonomous system that could incrementally make these parts. That's kind of where the general concept is. I think we'll get into some of the details of what our system looks like here in a little bit, but getting to now that Air Force need. Maybe I'll start with kind of a more critical near-term need that a lot of our maintenance depots in the Air Force see right now. A lot of the fleets in the Air Force have mission capable rates, I think on average of about 70%, sometimes as low as 50%, meaning half of our fleet's in a state of repair, and we can't use these systems. And some of the traditionally forged components where we kind of press apart all at once based on especially design die is just really hard to get in small numbers, right? Oftentimes these forged components may have been made decades ago on these planes, and the system that made it's no longer around. So there's this entire reverse engineering process that would have to be done to be able to produce that part again. And so we're often looking at lead times of somewhere between 1 and 4 years to get a small batch of parts to fix those on the planes. And that's obviously with forging in the more traditional way, with kind of in a bulk press all at once. But we think with this kind of robotic blacksmithing concept, right, we can drive that down. Even if it's a mixture of maybe it's additive with forging plus a little bit of surface machine to get the surface finished, bringing that down from a year lead time down to a matter of weeks, that we could deploy these systems perhaps directly at the depots or small and medium businesses that could house these systems to produce parts more on demand when we need them in the small numbers that we have. And so that's the immediate need. But then just when you build these tool sets, I think it really changes the paradigm and how you think about designing parts that you need. And so I think if we prove these concepts out that we can get reliable parts, maybe we change the front end of how we design systems altogether, and we're going to be designing parts and systems completely differently. And this begins to affect kind of the front end of our life cycle process and how we design.
Hey, we're in the crucial creation now. This is fantastic. So I want to make sure we fill any gaps here. I want to go over to you, Mike. Anything else to add here about what this robotic blacksmith idea is? And also a question to kind of add on to it. A lot of people, I know we're going to get into this more, but people may have the question already, how is this different than, doesn't additive manufacturing answer this question? Like, what makes this blacksmithing different than, let's say, 3D printing a part?
Yes, I'll touch that question in just a second. I guess to pull on the thread Andrew was kind of saying at the end of changing the way we design things, or this being a good use case. In my mind, we sort of look back through sort of the historical sort of trends of manufacturing, and a lot of things started moving towards mass production, right? Back 50, 60 years ago. And a lot of things come along with that, right? You start optimizing the equipment and designing things to make lots of things, right? And so you get really specialty equipment, and then it can only make that one thing. And it really affects our supply chain. We saw a lot of that with COVID, right? In the past couple of years, that when you need to make a pivot and do things a little different, it is not easy to change those really rigid supply chains that we've created, largely because we're trying to make lots of things. And that's inherently, as Andrew mentioned, something that is not really how AFRL does, or the Air Force, I should say, in the larger sense, does business, right? We don't make the same number of airplanes that, say, Honda makes of Accords, right? It's just different. And so we kind of sacrifice this ability to make things quickly at quality when we move to mass production. And I think we kind of left those things for artisanal craft people to do, job shops, individual workers, but then they become expensive, right? And so I think this is we're at a time in manufacturing now where we can look at how do we marry together robotics and simulation and controls and our knowledge of these classic processes and do them in a different way, more incrementally, use data to drive them so that we can get the best of both worlds. We can get the efficiency, the speed, and the cost of mass production, but we can get the flexibility and the creativity and the artisanal aspect of, say, the human sort of worker. And I think we're at a spot where we can try to do that because the confluence of events of computation and robotics and all of these things coming together at once. So I think that's just an exciting time, I should say. To your second question of why not just do this with additive, there are a lot of things about forging. We've been doing this for thousands of years, right? There's a lot of things we understand about forging. We know it gives really good properties. That sort of term forged in fire in the show is that's a saying of like, things get better often when they're forged in fire, right? I mean, that's kind of the point of the name of the show. And so we know we make good quality components, good quality material when it's worked and it's gone through that process. And we don't know that yet about additive. There's still a lot of questions about how additive components perform because it's a somewhat new process, certainly in comparison to forging. So I think there's a lot of components that don't need the geometric complexity of that additive brings, and we can benefit from the good quality process that is forging. So I think it's an exciting time to kind of relook at some of these old processes with a new eye.
Okay, I like this. So I've got another idea has already come to my mind, but I'm going to put that here, put it in the side shelf for a moment, because I want to hear what you're thinking, Nate, about, again, here, how this all fits in the greater Air Force, AFRL mission, what the project's all about. Then after, I want to hear from you what the history of this project is, like how it all started and how we got to this point.
So I'll just add a little bit onto what Andrew and Mike said. I think they pretty much covered a lot of the value proposition that we see for robotic blacksmithing or metamorphic manufacturing. There's lots of ways it's contextualized. The two of the things that I kind of fall back on that we haven't heard yet is that the process uses commercially off-the-shelf available equipment. If I wanted to forge something that was, I don't know, the size of a typical table or a wing spar or a whatever, kind of, you name it, bigger than you can pick up with your bare hands, the forging press that you need to make that part, you can count the number of them that are available in the world on your hands, or at least your hands and toes, right? There's not many of them, which goes to the why does it take 2 years, 18 months, 4 years to get a part, especially if you haven't ordered it for a few years. You got to use the dies, you got to qualify the system, you got to find an available slot on a forge press, right? All that stuff happens slowly. With robotic blacksmithing, metamorphic manufacturing, it's a robot that you could go buy tomorrow, right? I could cut a PO, put one in the back of my truck, drive it to the manufacturing site or the Air Force depot, install it. I could do the same with, a 20-ton forging press, a furnace. All the things that we need are small because it's, to Mike's point, it's all incremental. It's not one hit, one wonder. It's a whole bunch of little hits. It's swinging that blacksmith hammer over and over again to create the shape you want. The other thing that both alluded to, I think the concept of robotic blacksmithing is that you make the part that you need. You don't pick the part or the properties out of a book. It's a bit cliche, but it could in time change the paradigm for how we think about part. I need landing gear and I need it to be forged. I need landing gear and I need it to be forged to land on sand versus landing on a runway versus landing on a grass runway, right? You could start to make the components for the application. They're not going to be in a pick table somewhere. They're not going to be in a book or a spreadsheet, but you could use the system and the microstructure and the deformation to create the parts you need for any given application. It's hard to conceptualize for a material scientist or an engineer because that's not how we've been trained. We pick, right? We pick tools or we pick materials. We don't design them in process.
That's a fascinating element there. Sorry, before cutting to the story, I had no idea that was how a bigger shift in kind of how you guys approach things. That's pretty incredible. I'll get to that in a moment, of course. I want to hear the history of all this, but just want to sit for a second to say that is so neat how that does shift how you guys approach these issues. But what an exciting way to do it. You guys get to be designers to answer bigger problems. That's awesome.
Right. Yeah. Very exciting. The future is hard to envision.
Yeah.
Sure, yeah. But I want to go back to you then, Nate, about so let's go back to the history of this then. We have an idea of, again, what's going on here. We're going to get a better visual and kind of what the future may hold. But let's, again, look to the past. So what started this whole idea? When did it kick off? And how's it going now to make this robotic blacksmith dream come true?
Yeah, so I did do a little bit of research. I didn't remember the dates, but 2016, Dr. Glenn Dane, who we'll probably mention his name a couple more times throughout the podcast, he had this idea of robotic blacksmithing. He came to me, he said, hey, you've got CDME. Is there a way that we could put this together as a project? And at the time, it was a very simplistic idea, not the idea that was novel at its time. Today, it looks dramatically different than where we are. He was thinking, let's take some robots, let's take some forging presses or some ability to impart deformation and program them to make parts the way a blacksmith would make parts. So it was kind of the exact reincarnation of a blacksmith as a robot. The project was initially proposed and funded by LIFT, which is Lightweighting for Tomorrow. It's a Department of Defense Manufacturing Institute, or Department of Defense funded Manufacturing Institute. That program was the first time that robotic blacksmithing as a word was kind of out in the ethos. Worked really well. We ended up doing a competition where we had students across the country competing and building their own little robotic blacksmithing cells. That led to another project that was funded by AFWorks, which is a SBI or was or is the SBIRS TTR program within the Air Force. That was a joint project with Colorado School of Mines, and the faculty member there, just to give credit where credit's due, is Kester Clark. In that program, we took it one step further and we thought, what if instead of a robot, we had kind of custom manipulators? So a robot is a close proximity for a human, but they're not maybe necessary for robotic blacksmithing. So it was more of a study to see what other types of manipulators we could use. Jump forward to 2020, Mike Groeber sitting next to me here and Glenn, they had what, at least in my mind, was the epiphany of, why are we programming? Why aren't we doing or using machine learning and AI to figure out how to blacksmith, right? Kind of impart all the knowledge that humans have had for the last couple thousand years, impart that into an algorithm and let the algorithm figure out the path. As soon as we started saying those words out loud, everything changed. Right? Like that was a grand moment where you could start designing materials for the application in process of manufacturing. And then that led to a handful of awards with the Advanced Robotics for Manufacturing Institute, another DoD manufacturing institute, in collaboration. I think all, or at least most, or all of those programs were in collaboration with Andrew's team at AFRL. And then 2022 was the next really big step. So now I look at it all on paper. This was a really fast timeline. 2022, Glenn, again, Dr. Glenn Dane, he came up with the idea of, what if we expand this idea beyond just blacksmithing? What if it was, you have a blacksmith, but you also have a machining center and a painting center and maybe a boxing, right? You have welding, right? Any manufacturing process that you can think of, why can't they all be integrated at the point of use? If you've got a machine learning algorithm or an AI algorithm that's figuring out when and where to do things, you could effectively make anything, anytime, anywhere, if you had all the tools being controlled by this algorithm. And that concept, Glenn was successful at winning a National Science Foundation ERC, that we now call HAMMER, which is Hybrid Autonomous Manufacturing. That's our big push, kind of the envelope around this concept.
It's amazing. And also, I mean, look, thinking of historic precedent, thinking about, let's say, armies in the march needed to have their weapons, things equipped, fixed, whatever. They had to bring entire cities to make that possible. Workshops, they have to build up in all these locations. And to think about approaching this workshop approach, like you had said, from welders to forgers to painters, and to make that accessible at a base, let's say, I mean, what a fantastic idea. And I'm curious, too, you mentioned the algorithm. So first, when you were working this to train the system on like different ways to forge and learning these techniques, how did that work? Were you feeding it videos, or were you feeding it different? Like, how was it being taught, I should say, the algorithm, how to forge or become a blacksmith?
Yes, I can jump in there and add a bit of those details. So we're still pretty early on in that sort of learning let's call it the policies is kind of the term that people use, learning the forging policy that, say, a blacksmith would have in their head. That's a pretty complex policy. Right now, I would say the kind of colloquial term we use here is we're still making shapes, right? Like, we're just trying to push the material into the sort of geometric shape that we want it to be. But I think we've all kind of hinted around it in this discussion that that's not really the end goal, right? And that's actually one of the benefits of doing incremental forging versus, say, a closed die forging, where the material moves to fill in the die that you've created. So your sort of strain paths in the material are inherently married to the shape you're trying to make. So you kind of get the material properties you get because you made that shape. But if you think about a blacksmith or go way back to, like, say, samurai sword makers are a great example. They didn't just take a rod of steel and just hammer it right into that shape. They fold it over multiple times and draw it out and do things. And they're doing that to get a certain path to get the performance quality, right? Because if your sword's not of good quality, you're not a person for very long, right? If you're a true samurai. So you're trying to not only make a shape, but make a component that performs to some goal, right? That's where we want to get. That policy is much more complicated, and we're still working that, right? As Nate mentioned, we're still really early on in the life cycle of this technology. But right now, we're largely focused on taking images. So this would be, hit the material, present it to a camera, get a 3D reconstruction, compare it to the geometry you're trying to make, and then you have sort of algorithms, largely at this point still fairly human understandable, that are trying to drive that material towards the final shape. But ultimately, maybe the straightest path you could take isn't really the right one, because it doesn't give you the performance requirements that you need. So all of that is still very much ongoing.
You touched on an important part here that I think all of our listeners have questions now is, okay, we've been talking about the idea behind this, why we're doing this. What does it look like? I think a lot of people are imagining a full mechanical man with a hammer just hammering down on an anvil, creating this, like an automata almost. I assume that's not the case, but I want to start with you again, Mike. What does the system look like and how does it work?
We have chosen not to go that route, largely because I think some of the humanoid robots just look creepy personally. But and I'm not sure why we love to put like faces on robots and things, but that's a different discussion, I suppose. But no, Nate kind of mentioned that this is all sort of commercial off the shelf stuff. So when you walk in and you see the system, it looks like a bunch of things you would see in a job shop, maybe even an advanced metal worker's barn or something like that, right? It's a robot. It's a sort of what's sold as a manual forge press with a foot pedal. It's been set up so that we can control it with a computer. But these are fairly small presses, a robot, a box furnace, an induction coil for faster heating. But they're things that you would just sort of you wouldn't necessarily know this is a robotic forge cell when you walked in the room. And some of that is because we want it to be commercial stuff that people can buy and put together, and cost then is going to be a lot lower, and it's going to be more maintainable by a sort of more average person. It also makes it more transportable. So Nate, sort of mentioned taking this to a forward deployed base or something like that. One of those ARM projects that Nate was talking about, we quite literally did put a robot and a forge press and a furnace in a box truck, and we drove it to Georgia. There were tons of devil went down to Georgia jokes on the way, but we took this thing down, bolted it back together down in a weld shop down on Robins Air Force Base, and within 3 hours of parking our truck in the parking lot, we were forging metal. That just shows that this is transportable, and that's really something that is important to us. It's not about how it looks; it's about what it can make, right?
The concept that you guys could take it down to Georgia and had it work that quickly. Oh my goodness. So I want to jump over to you then, Andrew, and let's talk about not only the appearance now, let's kind of connect to it. What does it look like while this thing is testing? You said it's kind of like making shapes currently. Are you feeding it raw materials and it's just hammering things to shape or molding it? What does a standard test day look like when you're running with the robotic blacksmith system?
Yes, and it's been evolving quickly over the past couple years. There was a initial goal in one of the first project phases to make it very deployable, develop it in the university lab, take it down to Georgia, and so maybe constrain some of the system choices. So, we had a small laboratory oven that would heat the component up. It'd have to sit in there for a couple hours to get to a temperature that made it easy to forge. So you got a single robot arm that's reaching into that oven, pulling that part out, starting with a simple rectangular prismatic shape to start out with, and then there's a kind of target geometry that it's going to mold into. Generally, after it's pulled out of that oven, it's kind of going between two stations. There's an imaging station to be able to cap what that current shape is, because it's changing over time. Granted, there are modeling simulation softwares where we can begin to predict, if we press it in this way, how it's going to form. But models aren't perfect, so having a kind of ground truth of what the actual shape is. We've got that imaging system there to help us. And then the robot arms, taking it from there, putting it in a 16-ton pneumatic forge press. It's exactly what you'd see in an artisanal blacksmith's workshop today. The one we've been using up till now has customizable dies you can put into, from two simple flat plates to a curved edge, begin to kind of imprint that deformation in a certain way. And originally had a small robot arm, for transportability again, that was doing that motion in place. But yeah, and kind of the iteration process, right? We go from doing a few presses, going to the imaging system, seeing where we are, have that simple kind of shape making algorithm Mike described earlier, deciding where we need to hit next to increment towards our target shape, continually increment until we reach the target shape. Critical themes in the initial system was really just, it would work, but the speed, given some of the initial choices, could be kind of slow, right? We may be forging for weeks, small bits at a time until we got to that target shape. And so the next phase of the project was really about increasing that speed. Yeah. One of the key challenges affecting speed in the beginning was the selection of a small robot arm. So we had to add a sensor at the end of the arm to be able to sense some of the forces that were coming from the press into the robot arm, because the robot arm, while it was small, it could not sustain a lot of force back into the arm or it would break. So we were having to continually compensate the position of the arm to kind of relieve these forces as it's being pressed. And so every press was pretty slow given all these kind of real-time updates that we had to make. So that was one aspect of it. And the other one, if we put it back in the oven, it's then a long heating cycle as well to get it back to a formable state. So the next phase was really, how do we maybe sacrifice a little bit on fitting on a box truck to easily get down to Georgia, but how do we, if we're going to maximize speed, what is our closed cell to begin to look like? So move to a robot arm it's the same, really quite a lot of force with just a little bit of passive adjustment on the end, along with an induction furnace that could heat ferrous metals like steel in just a couple of minutes up to a pretty high temperature, get even much more deformation with a single hit. And so, that's kind of adding in the direct continual loop. It's kind of, heat, press, go image again, and that repeat that process over and over until you get close to the part you wanted. Yeah, and while it wasn't a one-to-one comparison, even just in the past year, we've managed speed ups of, we think, at least 100 times from kind of that initial prototype system that we took down to Georgia.
Okay, that's awesome. So I'm glad that you guys were able to help outline here not only what this thing looks like, but how it operates and how tests can go. But an element here that I'm curious about, so I want to go over to you, Nate, is the human element. So when someone's actually working alongside this, first of all, any safety precautions, like, well, this thing's working, are we keeping it in its own space? Can humans work alongside it? And what part do you play in it? Or is it pretty much all automated? You just feed the material, just hands up, you come back in X amount of time, it's done.
Today, it's very interactive. So one day in the future, I think all of us hope that it's something that can kind of run in a Connex or run in a box, if you will. Today, there's a lot of interaction. So we push go, and then we kind of see what happens. I think it's actually the best part of the program, which I'll get to in a second. But yes, there's a lot of safety training. We haven't talked about it yet. The team that works on this is hybrid as well. So it's a lot of undergraduate students, graduate students, faculty, staff, research staff, customers, AFRL, other folks from the defense industrial base. Like, it's a team, and the team is largely not working from a laptop. They're in the lab. So there's a lot of hands, a lot of people, a lot of engagement, and we try to keep everybody appraised of the safety concerns, kind of do what you should do in that type of manufacturing environment. Going back to tying in a little bit to the last question as well, what makes the team and the project special, and the reason that it's gone so fast, right? 2016 to 2022, to have a functional prototype that we've deployed in multiple locations around the country on defense products is crazy. That's super fast. Part of the way we've been able to get there is we've got a smart team, so Mike and Andrew, but we also have this point of collision where you've got students that don't know what they shouldn't think, right? Like, as we get older, we kind of talk ourselves out of trying things because it's similar to an experience we had 20 years ago or 10 years ago. Undergraduate students don't know that, so they throw ideas out that we may not even know that we discounted in our head, and they're really good ideas. And then you have grad students who are able to research those ideas and figure out the points of failure. And everything at this research lab that invokes a whole bunch of collisions between multiple people from multiple backgrounds at multiple education levels has just been phenomenal. I don't know that we could have gotten where we are today without that. And it'd be great if we were smart and designed it that way, but I think it just kind of happened. Right? We saw opportunities and we leveraged them.
Yeah, I can build off that point a little bit too. I mean, Nate, I appreciate a little while ago, Nate outlined all that history. Like, from us at our kind of small research team at AFRL, like, we acknowledged that OSU had an idea that was building hidden Air Force needs, so we wanted to get involved. And there was a little bit of kind of strategy on the AFRL side, like we wanted to think about what would a distributed team begin to look like. Exactly hard to envision what that is, but it started. Andrew, how about you spend a couple days a week at OSU, right? But start making these collisions happen. Even before we had rallied around necessarily like robotic blacksmithing idea, but I was, engaging with people, figuring out where good ideas were. I began to see, through some of those leads, like, let's just get in the lab. Like, we don't have to be all working around the same experiment all the time, but let's be there. There's going to be students come and go with their busy schedule. Same with faculty, but like, let's try to position ourselves in the same space as much as possible. So like, when we reach those critical moments, when say the system is running autonomously as it's designed, we've got a handful of people of different backgrounds, like Nate and Mike have described, where we can all look at the system together and kind of collectively assess like what's working well, what's not. Immediately brainstorm on like what we need to change to make the system run better the next time that we kind of run into or turn it on for autonomous mode. So seeing great value in just like positioning yourself where a lot of good people are coming together. And what Nate's saying, I think that is a reason why we've been able to move relatively quickly. In addition to lots of smart people, good diverse background, young and old minds all involved in the project as well.
I mean, this really does paint itself. I mean, a good material needs to have the right blend of component parts to make it strong. And you guys have a multifaceted team that are blended together to make it stronger. Like, that truly is a really great way of putting it. I'm going to go over to you, though, Mike, and kind of see your perspective about the team composition, for one, talking about these students to people who are in faculty to AFRL and how that is strengthening this process and why you see it as important.
Yeah, so I definitely want to hit on that. And maybe let me start back at your original question of how this how the system works and how the person or people in the room, let's just say, whether that be at a forward operating base or in our lab environment, interact with the system. And I think that'll then bring me back to sort of answering your question on this makeup. Is I think we want to just see manufacturing re-envisioned a bit, right? So these even in these autonomous systems, I think certain things, especially once the system has demonstrated, I can make these types of objects. I've made them many times. It's only slightly different than a part that I've made in the past. It can run autonomously in a box, just like Nate sort of alluded to. But I think we want to see these systems, and exactly how we get there, we don't know yet, right? I mean, this is still technology under development. But I think we envision a day where these systems, you tell it to make something and it goes, I think I know what you mean, but what about this? And there's a negotiation, and the human is communicating with the system in some way. And the system, when it's making something, if it feels like, hey, this is going a little wrong, I'm going to reach out to the expert to weigh in. So it opens the doors for a lot of other things. How do we have natural human communication with robots, right? Can humans just talk to robots? And there's things we're very good at speaking to, a master, blacksmith can teach an apprentice, and they can just use words and point to things, and the person kind of gains the context of what they mean. How do we do that between people and robots on really sophisticated systems like these forging systems that might also be welding things and doing other stuff as well? And so I think we envision those kind of systems. That's how we're going to interact with our manufacturing systems in the future. I don't know if that makes it kind of like Jetsons-like, but I mean, I think we're moving towards those kind of things, right? Where things aren't so rigid, they're flexible, and the technology can adapt to what the people in the room want. So given that that's what we see in the future, I think that then says the makeup of the people in the room need to be a lot more multifaceted than maybe what's been typical in a manufacturing environment in the past, right? In the manufacturing environment in the past, you had skilled tradespeople and maybe some material scientists and some mechanical engineers like hanging out on the side doing some stuff. But now we're talking about computer scientists and roboticists and computer vision people and people that are actually maybe psychologists now. And how are we going to interact with these systems, and how is that all going to work? And so that's really the exciting thing in our lab. A lot of the people that work in our lab are computer scientists and electrical engineers, and they ask the questions that Nate's talking about. They go, well, why can't we just do this? And your first thought is, well, that's not how you forge things. And then you go, well, actually, we probably could do that. And well, but you'd have to think about this. And they're like, well, I've got 7 algorithms that can do that. So why I'm not worried about that part of the problem. And you start looking at the problem differently. And we definitely want it to be applied. We want it to be useful to someone. And DoD is obviously one of our customers, but we see other people as well. And so we love being applied. We love seeing our stuff actually go out and be useful to people, but just bringing together a lot of new ideas and new ways to tackle things is just really exciting. And so we have a fun time in the lab. And that's the other point that Nate made that's really important is this isn't all theory. We're not writing papers at the end of the day. We're like building stuff that smashes things, which is pretty cool too. Students get excited about that. And when they see stuff getting made, that's not what they see in their classes. They get the concept of making stuff, but when they come out to the lab, you see a different energy to these students, and it's really exciting. It makes us feel younger, and it's really cool.
I think if I can add a little bit, I don't want to steal too much of the thunder, but one of the best things that's come out of what Mike's doing, Andrew's doing, and then there's another couple dozen people working in the lab on similar and related projects that just aren't robotic blacksmithing. It's exciting for me to see every day that we're doing the thing that people can't figure out how to do, right? When I go to conferences and I go to workforce meetings and manufacturing meetings, everybody sits around the table and they talk about how are we going to get college age students or high school graduates excited about manufacturing. In the center writ large, we have 150 undergrads from over 40 different academic departments they're coming to us, right? They're walking in the door saying, can I have a job working in the center doing manufacturing stuff? And it's not a bunch of 20-year-old college male students, right? We're 47%, as of this morning, in the center, we're 47% female and underrepresented minority, which is, pretty awesome. The reason that they're coming is because what we're doing is cool, right? We don't have to figure out how to make manufacturing look less dirty. It's still forging, right? It is dirty. You go home with black on your hands and you are dirty, but it is way cool. And that's what's attracting the workforce. That's what's going to attract them into this market and this space going forward. It's not going to be painting the ceilings white so it looks brighter in a manufacturing space. We got to do things in manufacturing that are novel and advanced and differentiating, and that draws people to it.
But that said, you guys touched on a lot of really important elements here of collaboration, and I kind of want to bring that to a head. Starting with you, Andrew, why do you think it's so important that OSU and AFRL made the specific connection? Like with these institutions, what gives us the power to make something like this that maybe other partnerships wouldn't?
Yeah, I mean, there's one, I think, Ohio, the Midwest as a whole, Ohio State in particular, I mean, a strong history of manufacturing, material science. I mean, Ohio State has one of the only bachelors in science and molding engineering. There's a core specialty that's been in Central Ohio for a long time. So on the technical side, made a lot of sense. Yeah, on the other side, there were, I think, both sides saw the benefit of teaming up. And it wasn't just transactional. It wasn't just you bring your money, I'll bring my money, and we pull the money together. Granted, I think as technology develops, money naturally comes as you're successful. But yeah, there's just a belief that the team that's bought in, that trusts each other, that believes in each other, that we're building something successful. It's kind of that shared spirit that keeps everyone going. And there's just a lot of trust that was built up quickly, continues to develop, and keeps moving well. And I think, and to a point that was made up earlier too on like why it is successful, build off what seems to be working, right? So we started out like just get in the lab, right? So I was used to being in life as a computational modeling person, being at my desk in front of my computer in my own little office, being there all day, right? And yeah, the more I know, I introduced in my AFRL Inspire talk the idea of a nomad researcher, right? Like go where the interesting things are happening, go where the people are, go where things are actually being made. If we can get people to believe into that, like that's, I think where a lot of good is happening. So yeah, it's good. It wasn't just me figuring it out. I feel like collectively we've all been doing it together.
Andrew's leadership and I had a conversation probably 5-ish years ago, and we didn't talk about money. The whole idea was, let's figure out how to do some of our people at Wright Pat, some of AFRL's people at OSU, and get everybody together and I don't know, just effectively agree to go be awesome together. We never talked about an exchange of cash. That's something that as we found project opportunities, we started to go collectively go after money. But it never started with that. It was, let's do something different and be awesome.
But I want to dive over to Mike real quick to touch on this. Any thoughts on the OSU AFRL connection and what the importance of that is and what makes it truly unique?
I think there's just, there's a similar mindset that starts obviously with people. That's mindsets. People attribute them to institutions, but they're more about individual people, right? So I think there's a group of individuals that sees similar problems, wants to tackle them in sort of similar ways and enjoy working together, right? So that's like a requirement for any of this stuff to work. But I do think as a whole, OSU tends to be a fairly applied, research focused institution, maybe more so than, some other universities. And so we do a lot of industrial research, and maybe that's being in the Midwest, having ties back to the aerospace and the automotive industry. So I think that part's a natural fit. Obviously, proximity is really important. Having people like Andrew be able to come to the lab and be there. It's very different when even before Zoom became Zoom, right? People had phone calls with funding agents and industry partners that were across the country. And it doesn't have the same feel as when they're in the lab working with you. So I think there's that. And I'll just say, for me personally, I've just tried to keep the AFRL mindset when I came here to OSU. That when people ask what it was like to work at AFRL, the difference between the university, and actually it's pretty good here at OSU, but is everyone was definitively on the same team at AFRL. You couldn't not be, right? You worked together, and growing up playing team sports, all of those things I would much rather play a team sport than an individual sport. That's just how I personally am wired. And so when I came here, that was the thing I was most scared about losing from AFRL was that team mindset. And I found it in CDME and a handful of faculty members that happened to be the ones that then wanted to work this project. So maybe it's just dumb luck. I don't know. But when you find that, you don't let it go, right? You just say, we're going to keep the band together, and we're just going to keep going on tour, and hopefully people want to come here and play, right? That kind of thing. And I think if you show excitement about it, the students come, and then it's a snowball rolling downhill at that point.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AFResearchLab. And remember, stay curious.
Logging off.